finally, we come to what is probably the major motivation for power series, and that is Taylor series. And Taylor series is based on Taylor's theorem, which says the following. It says that if we have some point x equal to a, which is going to be our center, and we have an open interval about a, and there is a function that in this open interval, all of its derivatives exist. So in other words, the function is defined on the interval, the first derivative is defined, the second derivative is defined, third derivative is defined, and generally we denote the nth derivative by f to the n. It doesn't mean f raised to the nth power, but in this context it's the nth derivative. But every order of derivative exists. Then it's a fact that we can represent the function as a power series. Okay, notice that a very succinct way of writing this power series is as follows. We take the derivative at a, take the nth derivative a, divide it by n factorial, and have x minus a to the nth, where we define the 0th derivative as just being the function. Okay, so this is kind of a compact way of writing this power series. And when the center is 0, the power series is often called the Maclaurin series. Okay, so that's just something you're going to hear. I'm not going to use that a great deal, but that's what most people call it. Now, even though this is a beautiful theorem, notice that there's a problem with it, is that in reality we can't use it. We cannot compute the infinite number of terms that go into this series. And so instead what we have to do is we have to settle for being able to approximate the Taylor series by a finite number of terms. And so whenever we take the first n terms of this Taylor series, we call it a Taylor polynomial. We call it the nth order Taylor polynomial. Now, there is a problem with this. We expect that as we go out to successive terms in the power series, they're going to be less and less important to the sum. They're going to get smaller and smaller. And because we know that in order for a series to converge, the terms in this series have to converge to 0. So if we go out far enough, the terms in the series really aren't contributing a great deal. But the problem is, how do we know when to stop the power series? Okay, how do we know what ordered Taylor polynomial we should use? So here is a really important result. It's called the Lagrange's remainder form for the Taylor series. And it says, okay, if you have an nth ordered Taylor polynomial, so this is the nth ordered Taylor polynomial, we're taking derivatives out to order n, and we can see that this is a polynomial of degree n. The difference between the true function and the nth ordered Taylor polynomial is this remainder term. And the remainder term is written as this is actually the nth plus 1 derivative. Let me rewrite this. This is actually this. It's the derivative of order n plus 1 evaluated at c over n plus 1 factorial times x minus a to the n plus 1, where c is some number between x and a. Okay? And this is the remainder. So some people write it like this. It's the remainder for the nth plus 1 terms on at x, where a is the center. Okay? Now, this tells us the exact value of the difference, but notice that generally we don't know what c is. C is some number between x and a, and we have no idea of finding out what it is. So what we try to do is we try to get a bounds. What we try to do is this. We go ahead and we find the maximum of the nth plus 1 derivative, and I'm going to I'm going to call this C. I'm going to write this with C. Let me just, instead of using X, I'm going to use the Greek letter C for X. Okay, it's going to go like this, where C is any number between X and A. Okay, and if I can find the upper bound on that, then I can find the upper bound on the error. In other words, I can find the maximum that the error can be. Okay, let's call this M. Then this implies that the error, the remainder term, always has to be less than or equal to the following. Okay, so that's the idea. Okay, we want to find a bound on the n+1 derivative, and that bounds the error term. And this tells us that the error cannot exceed this quantity. And we know x, we know a, we know n, and we figure out this bounds, and this bounds the error. Okay. Let me show you a quick example. So suppose, for example, we look at the Taylor series for cosine of x. I'm going to leave this as an exercise for you to show that this is equal to 1 minus x squared over 2 plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial dot dot dot. And actually, in general, it's equal to this. This is a very good exercise to work out. Okay, let's go ahead and see what the error is if we approximate it by the first two terms. When x is, let's suppose that the absolute value of x is less than 0.1. Okay? So what we have to do is we have to look at the third term in the power series. Okay, so the remainder term looks like this. It's going to be the third derivative of cosine, which is going to be minus sine over 3 factorial times, and here we know that this is absolute value of x is going to be 0.1 cubed. This is x minus 0. Okay, so we know that when the absolute value of x is less than 0.1, the remainder has to be less than or equal to this. Okay, and I'm going to put absolute values on everything here. Now notice that sine, of course, is bounded by 1. So this whole thing is bounded by 0.1 cubed over 6. And we can go ahead and work that out, right? 0.001 divided by 6, and work that out. We're going to get 0.000, whoops. Okay. And so that's going to be the error. When we have x, the absolute value of x is less than 0.1, what this tells us is this is 0, this is minus 0.1, this is plus 0.1. This means that if we plot the cosine function, okay, which we know goes like this, it looks kind of parabolic. Let me rewrite that over. Okay. So the cosine may look like this. It's going to be symmetric, right? This is saying the difference between this and the Taylor, the second order Taylor polynomial, I wanted to do this in a different color. There we go. Okay. This difference is never more than this. Okay. And so this is how we figure out how good of an approximation we need. Okay. We can either put the range of values we're interested in about the center, and see how far we have to go out before we get a certain error, or we can use the interval and compute it from there. So let me just kind of illustrate what I mean here. Let me just kind of back up and re-say this. So notice that you can be given, okay, you can be given a range of x values, and you can ask what is the error for a given Taylor series polynomial, or we could just do the opposite. We could ask for a given Taylor series polynomial, what does the range in x have to be to get a certain error? So in other words, I could set my error from the beginning, maybe to say like 0.1, and then this would look like this. And then I could go ahead and I could figure out x. X would just be the cubed root of 0.6. Okay, so what we do really depends upon our application. And here we'll just compute that real quick. So this would be roughly about, oh, it doesn't look right. Yeah, 0.8. That's what I thought. Okay, rads. So this remainder theorem is very helpful in telling us when we should truncate a particular power series.